All right, so today we're going to look at section 2.2, okay, which is definitions and biconditional statements. So we're going to continue on with that idea of if-then logical statements. Okay, we're going to start out with a couple definitions that we can use to illustrate what we're going to do in this section. Okay, so here's a fact. Okay, it says two lines are perpendicular if they intersect to form a right angle. Okay, that's a statement that's true. Two lines are perpendicular if they intersect to form a right angle. Okay, and here's another one about perpendicular. This one has to do with what it means for a line to be perpendicular to a plane. Okay, so a line is perpendicular to a plane if the line intersects the plane in a single point, because we might have a line and a plane that are parallel. They might never intersect, so that wouldn't apply here. So specifically, for a line to be perpendicular to a plane, it has to intersect the plane in a single point. It also can't be a line drawn in the plane, because then it wouldn't intersect it in a single point. It would intersect it at every point. So it intersects it in a single point, and it's perpendicular to every other line you could draw in the plane. Okay, so here's an example. The way I show that it's perpendicular is I draw in that little symbol. The dotted portion, that's going behind the plane, or below the plane, so we can't see it. And then it's coming back out again on the bottom. So if I were to draw another line in the plane, okay, there's a line in the plane. That is perpendicular to the black line. Okay, the red line, you're trying to think 3D here. The red line and the black line are perpendicular. Any question on that? All right, so there's a couple definitions about perpendicular. Okay, the symbol that we use when we want to say two things are perpendicular, since that's kind of a long word, we don't have to write that every time. We use this T, capital T, that's upside down. So when we're writing proofs, when we're doing anything where we want to use the word perpendicular, it's perfectly fine to just use this symbol. It's like an upside down capital T. Anybody ever seen that symbol before? That means perpendicular? A couple people? Okay. So when you have a definition, okay, like the book gives you a definition of something, these statements are true in two directions. What do I mean they're true in two directions? I mean they're true if you read them forward, and they're true if you read them backward. So when you read it forward, that's the original statement. Does anybody remember what it's called when you read it backwards? It's kind of when you switch the if and the then. We did three different things, but this is the most basic one you can do. Just switching the if and the then. Katrina? It's the converse. So in a definition, the original statement is true and the converse is true. Okay? This particular fact right here always happens with a definition. Now, if something's not a definition, this might not happen. Let me give you an example. If x equals 3, then x squared equals 9. Is that true? If x is 3, then when you square it, do you get 9? Yeah, that's true. But if you switch the if and the then part, if you switch the hypothesis and conclusion, it's not true. If x squared equals 9, then x equals 3. Why is this one not true? Exactly. If x squared equals 9, You don't necessarily have to square 3. You could have squared -3. -3 times -3 is also 9. So this is not a definition because it's not true forward and backward. If it was true forward and backward, then it would be like a definition. Okay, so we had a definition above. Go back up to it for a second. It said two lines are perpendicular if they intersect to form a right angle. What I've basically done is I've rewritten that in if-then form. If two lines are perpendicular, then they intersect to form a right angle. Okay, that's a definition. It's just an if-then form now. If two lines are perpendicular, then they intersect to form a right angle. First of all, any question on how I put that in if-then form from what you had up above? Okay, since it's a definition, this statement is true, and the converse is true. So if we switch it around, switch the hypothesis and conclusion, it says, if two lines intersect to form a right angle, then they are perpendicular, or then the two lines are perpendicular. And that's true. Right, so anytime you have a definition, the original statement's true, and the converse is true. Any question why both these statements are true? Okay. So I want to try an example. It says, decide if each statement is true or false using the diagram below. Okay, so we've got two lines. It shows angle AXD as a 90. Okay, and that's all that we know. Do we know that any of these other angles are 90s? They're only given us angle AXD. But yeah, we technically know that all these angles are 90. Can anybody tell me how you know one of these other angles is 90? Luke?
If CXB are vertical to DXA, then
Yep.
it has to be 90.
Perfect.
Since that if they're supplementary, then 90 plus 90 also equals 80 on 180. So that means AXB also has to equal 90.
Okay, so there's two things he said. First, CXB is vertical to AXD. Right? So if they're vertical, they have to be equal. So we automatically know AXC is 90. And then he also said that, did you use the one above it?
Yeah. AXB is supplementary to DXA, so it has to be 90 degrees.
Sure. So DXA and AXB, they form a linear pair. Okay? They're supplementary. They add up to 180. If one of them's 90, the other one's 90. And then you could use any of those two arguments to prove that DXC is also 90. So you got 4 90s there. Right? We might not need that fact, but it's good to know. Right? DX and B are collinear. Okay, is that true or false? Ariel? True. DX and B, they lie on a straight line. So that's true. Okay, how about that one? First of all, can somebody just pronounce what all that says? A lot of symbols there. Ian?
Line AC is perpendicular to line DB.
Right. Line AC is perpendicular to line DB. Is that true or false? Go ahead.
Sure.
Yeah, that's true. AC and DB, in this case, they're horizontal and vertical. They've been marked with that 90. That's true. Okay, and the last one. Well, actually, I think Luke already said this when he was describing. It says angle AXB is adjacent to CXD. AXB is the one on the right. CXD, that's a vertical angle. Okay, we talked about that earlier. So that's false. AXB and CXD are vertical. They are not adjacent. Any questions on that? All right. So another form of a conditional statement is this only if. Okay, this phrase only if. You saw the phrase if and only if on the test. There were 2 multiple choice answers that had that in it. This isn't quite the same. This is just only if. Okay, so this says it is Saturday only if I am working at the restaurant. Okay, and I'm going to show you how you can take something that has the words only if and change it back to what we're more familiar with, which is an if-then statement. Wait, anybody have a guess what that would be equivalent to? Really, you've got two choices. You got the if it's Saturday, then I'm working at the restaurant, or if I'm working at the restaurant, then it's Saturday. It's one of those two. And once you know which one it is, you just have to remember that. Luke?
If I'm working at the restaurant, then it's Saturday.
It's actually the other way around. So we had a 50-50. So it's if it's Saturday, then I am working at the restaurant. So when you see the phrase only if in the sentence, and you want to change it to if then, you pretty much keep it in the same order it's already in. Keep the Saturday part first. Keep the restaurant part last. Now if I take out the word only, just taking out that one word makes a huge difference. If I say that, it is Saturday if I am working at the restaurant, that's totally different. You might think, well, what's the big deal? Well, in math, if you take out the word only, it's a big deal. So that switches it around. Now it would be what Luke said. If I'm working at the restaurant, then it is Saturday. Okay, so you got to read the sentence carefully and see, does it have the word only if, or does it have the word just if? And then you can use that knowledge to rewrite it as an if-then statement. Any question? So it's just something you got to remember. When it's got only if, keep it in the order it's in. So now we can take that idea and extend it a little bit to a biconditional statement. Okay, a biconditional statement has the phrase if and only if in it. Okay, our book doesn't use this abbreviation, but I like to use it for if and only if. They use this, I've seen this used before, IFF. It's if and only if. Again, you won't see that in our book, but if you want to use IFF to abbreviate if and only if, I'm okay with that. In geometry, we have lots of abbreviations, and we try to use them as much as we can. So basically, a biconditional statement using this phrase, if and only if, is a short way of writing the original statement and the converse all at once. So you don't have to write something like, if it is Saturday, then I am working at the restaurant. If I am working at the restaurant, then it is Saturday. We can combine all of what I just said into a single statement using this special phrase, if and only if. That's what it does. And I'll give you another example. Okay, so here's a kind of a generic phrase, A, if and only if B. Let A and B be any statements that you want. A could be, it is Saturday, and B could be, I'm working at the restaurant. Okay, but A and B are like variables that represent statements of a sentence. This is equivalent to saying, if A, then B, and at the same time saying if B, then A. So here's the original statement, and then here's your converse, right below it. Okay, so let's say I had the statement that I have right here. If it is Saturday, then I'm working at the restaurant. If I want to take the converse of it, it'd be, if I'm working at the restaurant, then it is Saturday. If I want to say both of those at the same time, I can say, it is Saturday, if and only if I am working at the restaurant. If and only if means I'm automatically saying the original and the converse all at the same time. So for a biconditional statement to be true, both statements have to be true. Okay, since a biconditional goes two directions, forward and backward. It has to be true in the forward direction, and it has to be true in the converse. If either one of those statements are not true, then the biconditional is not true. Okay, so it's harder for a biconditional to be true, because there's two things that have to be true, not just one. That's what I'm saying right here. Okay, another way of saying what I just said is the biconditional statement has to be true forward and when you read it backward. The original and the converse. Same idea. All right, let's look at an example. Okay, so this example says, rewrite the following biconditional. Okay, we know it's a biconditional, and this is how you know. Okay? If and only if. If you see that phrase in a sentence, it's a biconditional. Doesn't mean it's true or it doesn't mean it's false. It just means it's a biconditional. You determine if it's true or false right now. Okay? So it says rewrite it as its conditional statement and its converse. Okay, so take a second and see if you can try to break up this if and only if statement into two separate ones. If A, then B. If you get that one, then just switch it. Get its converse, and that's the other one. Okay, so see if you can split that into two separate statements. Okay, was anybody able to get the first statement? Splitting up that biconditional. If what, then what? Yeah, Connor?
If three planes are collinear, then they lie in the same plane.
Can you just say that one more time?
If three lines are collinear, then they lie on the same plane.
Yeah, good. So if three lines are co-planar. Yeah, I thought you had said planes the first time, three planes, but then I think combination of what you said was correct. So if three lines are coplanar, then they lie in the same plane. Okay, now all we have to do is find the converse, and we got the other one. Okay, what would be the converse of statement 1? Oh, Dakota?
If three lines lie in the same plane.
Good start. If three lines lie in the same plane. Go ahead.
Then they're coplanar.
Then they are coplanar. Good. Then they are coplanar. Okay, any question on that? Okay, one thing you got to be careful of is your subject. Notice he didn't say, if they lie in the same plane, then three lines are coplanar. That's a little awkward to say it that way. You can use the word they after you specify your subject in the if. So you do have to switch the if and the then, but sometimes you also have to rework couple words to make it make sense, that's perfect. Questions on that? I could also give you statements 1 and 2 and ask you to put them back together. Combine statements 1 and 2 into a single biconditional statement. Right? Well, the answer would be what the original question was. Okay. Actually, we just worked with this earlier. It says, consider the following statement. X equals 3, if and only if x squared equals 9. Okay, first thing I want to know, purely, is that a biconditional statement? Just, is it a biconditional? Yeah?
Yes.
Yes, that is a biconditional statement. Okay. What's the key thing you check to see if something's a biconditional? Katrina? Yep, if it has if and only if. Okay, again, you won't see that IFF abbreviation in our book, but it is used. Okay. Second part. Now I'm asking about the truth of that statement. Is that biconditional statement true? And remember, for it to be true, it has to be true in two directions, forward and backward. If either one isn't true, it's not true. How about Sarah? No, why? What is wrong with that? You're correct. Okay, so I heard you read it a different way. What she had said is x squared equals 9 if and only if x equals 3. That's equivalent to what you have here. Okay, if you read it that way, that's the same thing. X squared equals 9 if and only if x equals 3. No difference between that statement and this statement. But what is wrong particularly with this statement? Is there something wrong with the original statement? Or would there be something wrong with the converse when you rewrite it? Eric? All right, so we have a problem here with the...
With the original statement. Or with that.
Yeah, we have a problem with the converse. The original statement is, if x equals 3, then x squared equals 9. Sure, that's fine. If x equals 3, you square it, you get 9. The problem is with the converse. If x squared equals 9, then x equals 3. No, that's not true. If x squared equals 9, then x could have been negative 3. That's why the biconditional is not true. The converse has a problem. Okay? Any question on that? Okay. All right, so now I'm asking you to do exactly what I just said earlier. I want you to take these two separate statements. If B lies between A and C, then AB plus BC equals AC. And its converse. If AB plus BC equals AC, then B lies between A and C, and combine it into a single biconditional. Does anybody remember the name of this? We studied this early on. If B lies between A and C, then AB plus BC equals AC. Anybody remember what that's called? What are these things called? That's a segment. That's part of the segment. You're doing addition. Yep, postulate. Very good. This is the segment addition postulate. Okay. Which is a definition. Well, it's like a definition. It's something that's true. It's a fact. So both of these are definitely true. Okay, so try to recombine it into a single if and only if statement. So we're going to recombine these two statements into a single biconditional. Okay, so Eric, what did you have?
I put AB plus BC equals AC if B lies between A and C.
Yep, that sounds good. AB plus BC equals AC if and only if And go ahead, what was your second part?
B lies between A and C.
B lies between A and C. Okay, how many people wrote it exactly that way? AB plus BC equals AC, if and only if B lies between A and C. That's fine. Okay. What's one other way you could have written it? And it's the same thing. Yep. Yeah, if you switch up, it's not the hypothesis and conclusion, because this isn't an if-then statement. But if you switch what's at the beginning and the end, B lies between A and C, if and only if AB plus BC equals AC. Okay? So any question on taking two and recombining them into one? It's a little bit more specific when you're splitting it apart. You have to be more careful. Okay? If I ask you to split this apart, the first part, if AB plus BC equals AC, that would be the hypothesis in the original statement. Then B lies between A and C. That would be the conclusion in the original statement. Okay? So when you're splitting it apart, there is a certain order. What's the original and what's the converse? But not so much when you're recombining it into one. That's fine. All right, so I think that's good for section 2.2. Okay, so for tonight, on page 82, look at 3 through 27 odd, 33, 35, 51, and 53. And in your MCAS packet, do the first three questions. Okay, multiple choice, first three questions.